Hello everyone. Today I'm going to explain a very important circuit that is used with photovoltaic systems in many applications. It is called maximum power point tracker or MPPT in short. To be precise, this MPPT circuit is not essential part of a small photovoltaic system. Without it, maybe only 50% or 70% power available from a photovoltaic panel could be utilized and rest will be wasted as heat. Today I'm going to explain a very simple circuit that can be used as a maximum power point tracker with a small photovoltaic panel. I'm going to use a 100-watt photovoltaic panel, and I'm going to drive three different kinds of loads: a 12-volt DC motor, a 12-volt incandescent lamp, and a 12-volt lead-acid battery. And I'm going to show the importance of this circuit driving these three different kinds of loads. Whenever different types of loads are connected directly with a photovoltaic panel, the biasing point are away from the maximum power point. So a fraction of the available power from the PV panel is utilized. The rest of the power is wasted as heat or remain unutilized. To utilize maximum available power, we need a circuit called maximum power point tracker or MPPT in short. It ensures maximum utilization of the photovoltaic power under different load condition and sunshine condition. For a low voltage or low resistance loads like a battery is connected directly with the panel, the biasing point is lower than the maximum power point. We need a DC to DC converter. This is called a step-down converter, or more commonly called a buck converter. This converter makes the load bias the PV panel at the maximum power point. So the PV panel is now delivering the maximum available power. If the converter is made efficient, most of the power will be going into the load. For high impedance loads like a 110 volt lamp, if connected directly with the panel, the biasing point passes the maximum power point. Almost the full panel voltage will be seen across the load, and very little current will flow through that. Now we need a different kind of converter called the boost converter to boost the voltage from low to high. A boost converter with a variable duty cycle can act as a maximum power point tracker for this kind of high impedance loads. If we want a maximum power point tracker which delivers maximum power under all types of loads, we need a buck boost converter which matches both the low and high impedance with the panel's maximum power point. For this video, I will show only one type of maximum power point tracker which will match low impedances with the maximum power point of the PV panel. I will use a 12-volt lead-acid battery, a DC motor, and a 12-volt auto lamp as loads. I am going to show a manually controlled maximum power point tracker only to explain how it works. In the next video, I am going to show an automatic maximum power point tracker. In my last video, I did not show the experimental electrical characteristics of the PV panel that I was using. Here is the data that I got. The short circuit current was around 4.5 amps. As the angle of the panel was not perfect and the sunlight was not full due to some clouds, I did not get close to 6 amp. Due to some connection resistance, you can see it is initially not a flat line. It has a little slope. Due to this resistance of the connecting wire, I got this kind of characteristics. Measured maximum power point is located at around 17 volts for the panel voltage. As I mentioned, that to match a low impedance load with the maximum power point, we can use a step down converter or a buck converter. Here is the basic circuit of a buck converter. It consists of an electronic switch. A transistor or a MOSFET can be used as an electronic switch. We need a fast recovery diode, an inductor, and a capacitor. A variable duty cycle pulses or PWM signal is applied to the base of the transistor. During the on time, the transistor conducts and the current flows to the load passing through the inductor. During the off time, the stored energy in the inductor flows to the load. The output capacitor filters out all the ripples due to the on-off process. Now, if the PV panel is connected to the input of this circuit with very low duty cycle, the biasing point is closer to the open circuit voltage. A very little power will be delivered to the load. With very high duty cycle, the PV panel will be biased around here. In the middle somewhere, we will be able to bias the panel at maximum power point. For an automatic maximum power point tracker, this process of hunting the MPP is done by the MPPT itself. Here is the practical circuit that I am going to use to track maximum power point manually. 555 timer IC generates pulses whose duty cycle can be adjusted using the potentiometer. This MOSFET is used as an electronic switch. The transistor pair is acting as a MOSFET driver. The frequency of the pulses is around 50 kilohertz. This is the photo of the buck converter, which is to be used as MPPT. I made the panel mount out of some aluminum extrusion pieces. The panel mounting angle is around 38 degrees. For British Columbia, Canada, this is okay. Ideally, in summertime, it should be around 35 degrees, and in winter time, around 65 degrees. This is the test setup to drive a 12-volt DC motor. This is the test setup to drive a 12-volt auto lamp. And finally, the third setup to charge a lead-acid battery. The test setup is shown here. You can see a motor is running, only motor is connected for the initial test. And this is the voltmeter and this is the ammeter measuring the voltage and current from the panel. And here is the setup, first setup with a lamp. A 12-volt auto lamp is connected with the panel and through the maximum power point tracker. You can see I'm changing the PWM of the PWM signal of the maximum power point tracker, and you can see the light intensity goes up and down. Initially the duty cycle was low and then go higher, and then even if the duty cycle is going higher, the lamp intensity goes lower. So there is an optimum point when the biasing point reaches the touches the maximum power point. Now a DC motor is connected. The panel, the maximum power point tracker, and at the output the motor is connected. So I'm going to change the duty cycle, adjusting the potentiometer, and you can see the voltage and current and the speed of the DC motor. As the DC motor is not loaded yet, so the effect of maximum power point tracking is not very prominent. If the motor were loaded, then we would have seen that the motor speed is the maximum at when the PV panel is biased at the MPP. You can see the effect to some extent, but not that prominent. So when it is biased at maximum power point, the voltage is around 18 volt and current is 1 amp. So though the PV panel can deliver even higher current, but as the motor is not loaded, it is not utilized. Now I am going to charge a 12 volt lead acid battery with the panel, and the setup is shown here. You can see a small 12 volt lead acid battery on the left, and as I am changing the duty cycle, you can see the voltage and current coming off the panel. So as the duty cycle is going up, you can see the voltage is going down and the current is going up. So you can see the minimum voltage you can go, that is 16 point some voltage. We did not go below 15.8 volt.